Thank you. And I would like to thank the organizer for giving me the opportunity to present this talk. I have to apologize that I'm coming only on the last day of this important symposium. At Caltech, our Theoretical Physics Institute was actually co-hosting a symposium to celebrate the 100th anniversary of the prediction of the gravitational waves. And it turns out that it was also a celebration of the detection of the gravitational wave, so I had to be there until last night. I think I met Professor Nambu first time when I was my first year graduate student, I think 1984, but I didn't have time, I didn't have nerve to actually talk to him directly, but I got to know him. I had an opportunity to get to know him more. I think when I went to the Institute for Advanced Study as a postdoc, 88, I was invited to give a talk in, I think it was September or October, and I think I gave a talk about the elliptic genus of case 3, which was, well, I was writing a PhD thesis on it, and I remember discussing with Emil about it. And then in December of that year, I got a phone call from Professor Nambu, actually asking whether I'd be interested in a faculty job at Chicago. It's so honored to get a direct phone call from him, so I almost immediately accepted it, but even without offer. But and then I spent a couple of years in Chicago, and it was very nice. And Professor Nambu often invited me to come over to his office, and actually he told me what he was working on. Sometimes I couldn't understand, but it was had a very important influence on me. And after that, after I actually went back to Kyoto, but we exchanged annual letter, and so basically I'm writing to him what happened, and he actually wrote me also some letters. And these are photos from Toru Eguchi's 60th birthday celebration in Kyoto. I guess this is his, he was giving speech on that occasion. And when I got the Nishina Memorial Prize, he actually wrote me a very, very nice letter, and it was very, very kind letter, and also remembering what the time when he actually got the prize, etc. And so in 2013, I went to actually Osaka University to give seminar, and he said he intended to actually come to the talk, but there was some problem, and he couldn't come. So, but he gave me a phone call after my seminar, so we chatted a little bit. That was, I think, like 5 years after I saw him in Eguchi's birthday. And last year, I got a message from Higashijima-san, who's a vice chancellor of Osaka University, saying that Professor Nambu is quite ill, so you should go see him. So I went to the hospital, and in fact, I think John was there. And we spoke for about half an hour, and he was actually quite cheerful. We talked quite a bit about some recent physics, and also he actually told me some anecdote of Marie Guerlain, but he said, "You never share that with anybody else, so I can't tell you." I miss him, and I'm honored to be able to present this talk today. So I'd like to actually talk about swampland. And swampland is a class of low-energy effective theory which cannot be a low-energy approximation to consistent quantum theory of gravity, such as string theory. So if I formulate it in the question in this way, landscape is a low-energy effective theory of consistent quantum theory of gravity, and swampland is its complement. So it's just defining it in different way. But this is a different way of posing questions, because whereas in landscape, people are trying to actually construct the example by using flux compactifications and various other constructions to come up with the example of low-energy effective theory, which comes from string theory or other construction top-down. And whereas here we are interested in understanding what are the conditions that if you have that, then you can clearly see that such theory cannot be realized. So if you like, we can say that landscapers are interested in sufficient conditions for consistent UV completion, whereas today I will be talking about necessary conditions for UV completion. So if necessary conditions are not satisfied, we say that those theories are in swampland. So there are various constraints known. So before I get to the main thing that I want to talk about, I'd like to actually briefly review some of other things that are known about characterization of swampland. And one of which is about low energy symmetries. So I have actually taken this from the paper by Nati Zyberg and Tom Banks, where they formulated it by combining various things that were known and also adding new things and formulated it in this coherent way. So one important feature of low energy effective theory of consistent theory of gravity is that there are no global symmetry. All symmetry has to be gauged. And otherwise, it seems to lead to inconsistency with various property of black hole and its evaporation. And all continuous gauge symmetry except for the one that is U1 or R has to be compact. And so this is also interesting. The spectrum of electric and magnetic charges form complete set consistent with Dirac quantization condition. So this is quite different from the talk we just had from Greg Moore, where you seem to get some interesting constraint on the BPS spectrum in field theory. But if you couple it to gravity, they are bound to have a complete set that are allowed with Dirac conditions. All point in the lattice has to be realized, and this is again motivated for example, in the paper by Nati Zyberg and Tom Banks, based on various constellations of black hole. Recently, Daniel Harrow actually wrote a very interesting paper using ADS-CFT correspondence to actually give another argument for this conjecture. And in this context, actually, you can actually derive some of these conjectures. And actually, I'm finishing a paper with Daniel generalizing some of his observations. So I hope to have a chance to discuss this in more detail in some other occasion. There are also various interesting constraints on the moduli space of string theory proposed. And unlike the case of symmetry, some of the statements are not really sort of derived from fundamental principle, but actually sort of observed based on known constructions. And I'd like to tell you a little bit about those. So before I get to that, actually, this is there is also some of what I'm going to say is related also to the issue of symmetry. So for example, the constraint, some of the interesting constraints on the moduli space come from attempt to derive inflation model from string theory, and in particular, try to construct a model where you have a scalar field with fairly flat potential, where a scalar field can travel in distance greater than Planck scale. And one attempt in doing that, so when you have a very flat potential, one way to enforce that is to assume that there is a symmetry, which requires the potential to be flat. And one example is natural inflation, where you make use of axiom, and you would like axiom to be inflaton. But in fact, in actual string theory construction from top down, by the work by Banks and collaborator, and also Sverchek and Witten, it appears that it is very difficult to construct action inflation model where action can travel greater than the scale set by a Planck scale. And there are some indications that this is related to this type of constraint on the symmetry, that there is a tension between the requirement of the symmetry, which enforces the action field to have almost flat potential, and the difficulty of implementing global symmetry in quantum theory of gravity. So here, actually, I'm just going to talk about the moduli space of low energy effective theories that is actually describing the stable vacuum. And there are actually various interesting proposals involving moduli of unstable vacuum, such as axion monodromy models. So some of what I'm going to say do not apply to these cases. So several years ago, about 10 years ago, Kumran Baffa and I actually formulated a set of conjecture about the moduli space of stable vacuum based on various examples of known string theory constructions. So for example, we conjecture that moduli space of string vacuum, if it is non-empty, has to be non-compact and complete, but has finite volume. And this seems to be the case for all known examples. So non-compact and finite volume means that it's sort of elongated toward singularity often. And in fact, if we move a large distance, well, complete means that that you can actually reach to. So there is a point where you can actually. So there is an infinite distance point that you can add to. So here is an example. For example, when you have a moduli, and if the moduli travel for distance t, then relative to the original point, then you get a tower of light particle whose mass is exponentially suppressed as t goes to large for some constant a. And another interesting observation, which seems to be true for all known examples, although we do not quite understand its physical implication, is that there seems to be no non-trivial one cycle with minimum length. So it's always sort of one cycle always shrink to a point. And in fact, all these statements turn out to be true for four-dimensional theory with n equals 3 or higher, as recently was shown by Sergio Secotti in his textbook on supersymmetry. There also seems to be some constraint on the type of moduli space, and this is again based on examples, and it'd be interesting to understand. There seems to be actually, for example, there seems to be some kind of bound on the total Hodge number of Calabi-Yau space, which you can think of as a mathematical conjecture, but it's sort of based on various observations. So for example, here is a result of my work with Christoph Keller, 2012, and this was actually sort of strengthened later by Christoph and Dan Friedan collaborators, where so we actually looked at the conformal field theory whose target space is Calabi-Yau space, and look at the implication of modular invariance. And so here is what we found. So if I take the total Hodge number of Calabi-Yau, in the case of Calabi-Yau threefold, it's H11 plus H21. And then the vertical axis is a conformal dimension of operator, actually H plus H bar. And what we found is that if you require a modular invariance, then there is always some non-chiral operator appearing below this curve. And this curve looks like flat, but in fact, as the Hodge number grows, it actually goes to 0. So that means that as Hodge number total Hodge number grows, the density of operators, so low-lying operators, seems to increase. And also, I don't have time to describe to you, but there seems to be some qualitative change in the behavior of this upper bound around Hodge number 500. And interestingly, this seems to actually fit well with some of the recent results by Wattie Taylor and collaborator. This is one with Wang, I think his student. For example, so this is for Calabi-Yau, I think this is for elliptic Calabi-Yau threefold, and this is fourfold. And so basically they are plotting all possible Calabi-Yau of this class. And there seems to be some kind of thinning out for a total Hodge number around 500. And they have some set of arguments that says that this type of Calabi-Yau is actually the one which saturates the total Hodge number. So it's actually it would be very interesting to understand whether there are actually constraints on the topology of Calabi-Yau, because of course this would have a very important implication on the structure of landscape. Whether actually it has finite component or infinite component would be very interesting to understand. Now, the main thing I would like to talk about today is implication of consistency of quantum theory of gravity on property of energy momentum tensor and other energy condition on the low energy effective theory. And of course, in gravitational theory, we often employ various energy conditions and prove theorems, such as you require null energy condition or dominant energy condition, and using that to derive a property of solution to Einstein equations, such as singularity theorems and area theorems, etc. But often these energy conditions are postulated in the beginning. And one can ask, are these conditions required from the consistency of the theory? So I would like to show you some example of energy conditions that actually are required by consistency of gravitational theory. So I would like to discuss that in the context of, again, holography. So suppose you have a low energy effective field theory whose gravity solution are asymptote to untitled space at infinity. Then the ADS-CFT correspondence says that such gravity theory has to be equivalent to conformal field theory on the boundary. So the question is that assuming that conformal field theory on the boundary is consistent and has a positive Hilbert space with positive definite inner product, can you infer some condition on the bulk gravitational theory in the low energy limit? So that's the question. What does the consistency of conformal field theory means for the gravitational theory? So here I will focus on information theoretical inequality that you can derive from consistency of the conformal field theory, and ask what do these conditions mean for the gravitational theory. So this is a subject that has been investigated by many people, and so we're going to utilize their result to find constraints. So I'm going to talk about two set of works that I have recently done. And one is to use a consistency of conformal field theory to characterize gravitational effective field theory. So namely, which effective field theory can be coupled to gravity and have consistent UV completion. And this part is based on my work with Jennifer Lin, who was a graduate student at the time when we wrote this paper, Matilda Marcoli, and Bogdan Stoikov, who is my graduate student. He's graduating. And currently work in progress, and in fact, I'm supposed to be writing a draft on this one, which I should do very soon, with Nima Lashkari and Jennifer and Bogdan and Mark van Ramstong, which we hope to finish very soon. And the second part, I will talk about the converse of question, which conformal field theory has gravitational description with smooth geometry, and I will discuss some condition now on the conformal field theory side, which is the work that I did with Caltech graduate postdoc Nim Bao and a student and a postdoc at Stanford. So suppose you have a gravitational theory in D plus one dimensional untitled space. As I said, it's supposed to be equivalent to conformal field theory in D dimensions. So I would like to discuss a condition on entanglement entropy and the related quantity in a conformal field theory. So suppose you have a conformal field theory on the boundary, and suppose you pick some domain A. Then for that domain, you can define what is called the entanglement density matrix, which is the following quantity. Suppose you have a state on this conformal field theory defined on this space-like surface and call that as psi. And then I consider this state, and then I take trace over Hilbert space over complement. That's what I meant by trace of A bar. That is a trace over Hilbert space on the complement of this domain. And this gives you some positive definite matrix whose trace is equal to 1. And this is an operator acting on the Hilbert space over this domain A. So this is the entanglement density matrix for this domain A. And for Neumann entropy, for this density matrix is called entanglement entropy. So this is a measure of how much quantum state associated to this Hilbert space for domain A is entangled with that on the complement. Now, in the famous work by Shinsei Ryu and Tadashi Takayanagi, it was conjectured that this entanglement entropy of the conformal field theory can be calculated by considering the following quantities. That suppose you have this domain A, and suppose you have asymptotically untheta space in the bulk, then you consider a minimum surface ending on the boundary of this domain, and calculate the area of this minimum surface and divide by 4 times g Newton. And in the limit of weak gravity, where the Einstein Hilbert action plus matter is a good low energy description, they conjecture that this entanglement entropy is approximated by this formula. And so this was actually recently derived from more fundamental principle by Maruda Senna and the collaborators. And so this is a way that you can actually translate this entanglement entropy computation in the holographically in the bulk gravity theory. So I'm going to use this. Now, entropy are known to satisfy various interesting inequalities. And this has been investigated quite a bit in quantum mechanics, in the context of quantum mechanics, and also quantum information theory, because it gives these inequalities often are useful to understand some kind of bound on the efficiency of information processing tasks. And so I would like to discuss various inequalities satisfied by entropies. And we'll find that some inequalities are satisfied both by conformal field theory by just requiring the positivity of the Hilbert space and standard property of quantum mechanics, and also by using gravity. But we also find that some inequalities are satisfied by any conformal field theory, but gives you non-trivial constraint on gravity, because it's not always satisfied by gravity theory. So that means that requiring this inequality imposes condition on the gravity theory. If gravity theory does not satisfy such inequality, then it can never be equivalent to conformal field theory. So therefore, we do not expect such gravitational theory to have a consistent ultraviolet completion. You can also have a converse situation where there are some inequality which is satisfied by gravitational theory, but may not be satisfied by conformal field theory. So that's also an interesting class of conformal field theory, because that can answer the question, partially answer the question of which conformal field theory has a description in terms of smooth gravitational theory. Of course, there are the fourth sets of inequality which are not satisfied by either ADS gravity or conformal field theory, but I'm not going to talk about these inequalities. So here is a sort of summary. So these are, you can think of this as sort of sets of inequalities, and in this Venn diagram. So for example, this is a set of inequalities satisfied by gravitational theory, and this is a set of inequalities satisfied by conformal field theory. And in this intersection here, which are inequalities satisfied by both conformal field theory and ADS gravity, the example of which is a strong subadditivity condition. Namely, that if you have 3 boundary domains in conformal field theory, then entanglement entropy associated to domain A union B. Also, when I write AB, I mean A union B. And entanglement entropy associated to B union C is greater than entanglement entropy for B and ABC. So this is known as strong subadditivity condition. This is rather non-trivial inequality to prove in quantum mechanics, But this is extremely straightforward to prove in the gravitational theory. In the gravitational side, this just follows if you use Ryu-Takayanagi formula from something like triangular inequality of the geometry. Whereas in the conformal field theory side, or more generally quantum mechanics side, this is rather non-trivial inequality to prove. Yes, you have a question?
So you're already assuming null energy condition?
I'm not assuming null energy condition. Indeed, it is true that if you require this for your formula, HRT formula, then this is related to null energy condition. Here, I'm saying that for Ryu-Takayanagi formula, this is satisfied for any geometry.
So you will just work with static configuration?
Well, I would like to clarify what here I will discuss which cases it apply to your more general formula, but here I'm only making a statement about this particular formula. So it is true. Thank you for clarifying this. So this inequality is always true for a Ryu-Takayanagi formula, but requiring this for HRT formula, which apply to time-dependent case, in fact, require some integrated version of null energy condition. So that is interesting because that would be an example of inequality of this type, where if the gravitational theory does not satisfy the integrated null energy condition, then even this is not satisfied in a time-dependent situation. So you can bring part of this into this side also. So thank you for clarifying this. And but here today I'll be focusing on some other class of inequality which come from the positivity and the monotonicity of relative entropy. And later I will talk about this side where you have a set of inequality that are always satisfied by gravitational theory, but may not be satisfied by general conformal field theory. And the monogamy of mutual information is an example of that. And so we will interpret this inequality condition for relative entropy as actually certain positive energy conditions. And here I will discuss how we can go about classifying such inequality, which I call holographic entropy inequalities, that are always satisfied by gravity theory, but are not necessarily satisfied by general conformal field theory. So let me first talk about this side. So, well, in general, even from the original motivation of the notion of entropy from 19th century, the energy and entropies are closely tied concept, and we will utilize that. So now first I'd like to discuss the concept of energy in the gravitational theory. So suppose you have some subspace of a space like Cauchy surface of the gravitational theory. So here we have in mind actually part of consider asymptotically untilted space. And suppose you have a domain and you have a Ryu-Takayanagi surface, then there is a region of the space which is sandwiched between the Ryu-Takayanagi surface and boundary domain. So I have in mind applying this concept to this type of domain. So please keep this in mind, but what I'm going to say in the next couple of transparency apply to some general subspace sigma of Cauchy surface. So now consider some gravitational theory. So we have a metric and some other matter field, which I'm going to just collectively write as G, even though G, part of that can be some matter field. So suppose you have some Lagrange density, then of course the variational theorem says that, variational property says that if you take variation, infinitesimal variation of Lagrangian, then it gives rise to equation of motion of the theory. And well, that is for the action, so that means that the variation is actually total derivative modulo equation of motion. And this total derivative part is related to actually the symplectic form of this system. I guess my pointer is getting weak. Can you actually see this, or is this too weak? Thank you. And so namely that if you have this symplectic form, then if you take, so this D is exterior derivative on the space-like section. So this is a space-like derivative. But you can think of this also as a one form in the phase space of the field theory. So you consider field configuration on this surface sigma. And you can think of this as one form on this field space, because this has to do with variation of the field configuration, the linear variation of the field configuration. So you can think of this as one form. So you can take actually exterior derivative in the field space and consider two form in the field space. And that gives rise to two form in the field space that is the symplectic form. Okay, so you have a symplectic form and Lagrangian. So you can consider defining Hamiltonian associated to this construction. So this is a standard Hamilton-Jacobi theory. So in general, if you have symmetry of the system, you can consider corresponding Hamiltonian, which generates a symmetry. So in a gravitational symmetry, gravitational theory, the diffeomorphism is always a symmetry, gauge symmetry. So you can consider Hamiltonian, which generates that diffeomorphism. So suppose you have a vector field, or this is a type, or this should have been C. Then you can consider generating diffeomorphism associated to the vector field, and then you can define Hamiltonian associated to that diffeomorphism. So this is a standard procedure. So this is something we teach in undergraduate classical mechanics. So I'm not going to repeat that. But the Hamiltonian is defined as a generator of this infinitesimal transformation corresponding to the diffeomorphism. The only subtlety here is that when sigma has, this domain has a boundary, then you have to take into account the boundary term, and you have to worry about the boundary condition. And in a good situation, so this is actually the variational formula for the Hamiltonian, but you can actually integrate this, this formula to define Hamiltonian associated to this diffeomorphism. And the boundary term you add is very important. And for example, in the case of pure Einstein gravity with Dirichlet condition, this can be a Gibbons-Hawking term. And so in each case, you have to, so it's not always possible. It requires, so it depends on the choice of sigma and xi, whether you can find such integral. But in the case that I'm going to talk about, there is such a boundary term that we can choose. So now I'm going to relate this Hamiltonian to entropy. And so again, I would like to remind you that entropy, entanglement density matrix is defined by taking trace over complement of the region you are interested in. And the relative of relative entropy means that you are actually comparing two such entanglement density matrices. So suppose, for example, I choose a vacuum state of the conformal field theory. It could have been other state, but I choose it to be the vacuum state. And then I take any state in conformal field theory. So here, this state and this state can be very far away from each other, but I just choose another one. So if you have a weakly coupled gravity description, this should correspond to yet another solution to the gravitational theory. Then you have two density matrices, one associated to vacuum and one associated to this new solution. So you can actually compare how close these density matrices are by computing relative entropy defined in this way. So, well, this is sort of introduced as a nice measure of comparing these two. This is not quite symmetric between rho and rho naught. So this is different from the distance. This doesn't satisfy the axiom of the distance, but it is positive. And also, if rho and rho naught are close to each other, then in the second order variation, this gives rise to Fisher metric, which is a standard metric in the space of these matrices. So this is a good quantity. And then, interesting thing is that this quantity has a nice holographic description when this domain it has a spherical geometry. So this part, of course, does have a nice description always, because you can calculate using a Ryu-Takayanagi formula. But if it turns out that if A is spherical, this part also has a nice holographic description in the following way, as a boundary energy. So if you have a holographic description, then the first term here is related to Ryu-Takayanagi formula, so it can be computed by evaluating the area of this surface. And then the boundary energy give rise to the second term. Now, it is actually by using the formalism that was introduced by Robert Ward and the collaborator here at Chicago, we can actually convert this entropy formula, relate this entropy formula to energy formula. So what we found is that you can actually choose a particular time-like vector on this domain so that you can actually write this relative entropy in terms of the energy integral. So, namely, that relative entropy can actually be, we can actually write this relative entropy as a quasi-local energy. And it is not so trivial to prove that in this case you can actually find such boundary term, but we can prove that such integral exists. And so we are able to show that this relative entropy is actually the difference between the energy for this solution and this solution. So this is actually interesting because relative entropy is known to be always non-negative. So it's not obvious from this expression that it is non-negative, but it is, that you can prove it for any consistent theory with positive definite inner product. And that automatically implies that the energy associated to this vector field in this domain, sigma, is always bounded by the vacuum energy. So this is an example of a positive energy condition. And this condition is actually not vacuous. So in the previous paper that we wrote December of the previous year, we actually looked at this in an infinitesimal case where you actually have the first non-trivial order correction to first non-trivial correction back reaction to the geometry by matter, in which in this case this condition actually reduced to some integrated positivity condition for the time-time component of the energy momentum tensor of the matter. There are actually another interesting condition you can derive. So we have seen that positivity implies some positivity condition for the Hamiltonian associated to particular time-like vector. But you also have a monotonicity for the relative entropy. That is that relative entropy is positive when you actually increase the size of the domain. So that gives rise to yet another inequality associated to another time-like vector tau. So here is actually the other time-like vector, which is actually a relatively simple form. So here, suppose you have this time-like constant Cauchy surface, time constant Cauchy surface, then you can choose a normal vector to the Cauchy surface. And then there is some function associated to foliation of the Ryu-Takayanagi surface, which I don't have time to explain. But I can use it to normalize this time-like vector. And then Hamiltonian associated to that has to be bounded below by the monotonicity condition. So we found that actually the positivity and the monotonicity of relative entropy implies the positivity of Hamiltonian associated to the domain, sandwiched between Ryu-Takayanagi surface and boundary. Yes, Mukunda, you have a question. Well, I guess it depends on which energy you are talking about. I'm talking about particular energy, and I'm not sure whether that agrees with the energy you are considering. So you can, of course, depending on which time-like vector you choose, you can define various different kinds of energy. So it's possible that we are talking about different energy, but it gives rise to various different types of energy condition for the matter sector, so that you can think of this as a condition for the low energy effective theory. There is yet another interesting thing. So here I consider the positivity conditions
and then I consider monotonicity to give rise to another condition, you can actually consider taking one more derivative and see what happens. And it turns out that if I take one more derivative, then it's actually reduced to integral of energy density over Ryu-Takayanagi surface. So this turned out, this I think is rather interesting. So because, for example, in the case of, at least in the case of solutions which are close to pure ADS geometry, then there is actually a radon transform and its inverse, which enables you to invert this relation and find the local expression of energy density in terms of variation of relative entropy. So namely that if you are able to calculate the relative entropy for various different domains on the boundary, then you can utilize this knowledge to invert this relation and find the value of energy density locally in the bulk. But of course, I mean, you don't expect the gravitational energy theory to have local observable, but one can actually, in the limit of weak gravity approximation, then you can define approximate notion of local observable using inverse radon transform of relative entropy, which I found interesting. In fact, yesterday, so at the conference at Caltech, which ended yesterday, we also invited a few historian, philosopher of science to give a talk about Einstein. And one of the subjects people talk about was, apparently after Einstein proposed the general theory of relativity, there was quite a bit of controversy among philosophers whether you can actually, it makes sense to consider a local observable in gravitational theory because of the general covariance. And Einstein wrote to them saying that, well, look, you can actually consider sending geodesic and then consider intersection, and that would define the position in a local way. So this is somewhat similar to this type of idea, that you can define a position in the bulk by considering relative entropy on the boundary, and by considering intersections of Ryu-Takayanagi surfaces, you can define a point in the bulk. So we see that the positivity of relative entropy give rise to various positive energy conditions in conformal when you interpret that in the language of ADS gravity and give certain constraint on the consistency. So in particular, if you have a gravity theory which does not satisfy these conditions, then you can call them in the swampland. I would like to spend the remaining, I started out a little bit late, but remaining, how many minutes maybe? 10 minutes. I'd like to discuss classification of holographic entropy inequality. So I will focus on this side of the diagram. Conformal field theory state with gravitational dual have interesting entanglement properties implied by Ryu-Takayanagi formula. So we'd like to characterize such property. And we'd like to do that using entanglement inequalities. So as I said, there has been lots of things known about the entropy inequality in both classical and quantum context. In the classical case, you have Shannon entropy, which is sum over probability times log of probability summed over all the states. And it has been proven actually relatively recently, 2007, that there are actually infinite number of independent entropy inequality for more than 3 configurations. And this seems to have very important implication on asymptotic performance for information processing tasks. In the case of quantum von Neumann entropy, the situation seems to be a little bit less well understood. In fact, for more than 3 regions, the complete set of independent inequality is not known, although there are some numerical evidences that number is infinite. So I will explain why people know that they don't have independent inequality. So I will tell you what is the kind of procedure we will use to judge that. But so let me since I only have maybe 7 minutes or so, so let me summarize what we did. So we actually constructed a finite algorithm to classify all holographic holographic inequalities, holographic entropy inequalities. And we proved that for fixed number of regions, there are only finite many independent inequality, which is in contradistinction to the cases of general quantum mechanical system, which there are some evidences that there are infinitely many inequalities. And we have been able to classify all the inequality for some small number of regions. And we found new sets of inequalities. So let me try to explain some of this. So I talked about holographic proof of strong subadditivity, but let me actually present it. So this is related to the question that Veronica asked about. So strong subadditivity says that the entanglement entropy for AB and BC summed over is greater than entanglement entropy for B and ABC. And this is easy to understand from Ryu-Takayanagi formula, because the right-hand side is sum of this and this, because these are Ryu-Takayanagi formula for these quantities, whereas entanglement entropy for B is here, and the entanglement entropy for A is here. Now, triangular inequality says that this is shorter than the sum of these two, because this place is constrained, and then area here is smaller than sum of the area here and here. So obviously, this is satisfied. It is a bit non-trivial if we try to implement it to your HRT formula in the time-dependent case, and indeed give rise to some condition on energy property in the bulk. But here I'm talking about Ryu-Takayanagi formula. Oh, by the way, so here actually I'm only talking about the inequality implied by Ryu-Takayanagi formula. So inequality for HRT is a totally different matter. So in order to describe the set of inequality, it's useful to introduce a concept of entropy con. So let me try to explain what it is. So suppose you have n regions, and then you consider entanglement entropy for unions and intersections of these n regions. So if you have n regions, in general, if they are if you consider they are unions, then you can consider 2 to the n minus 1 different types of region, because you can either have that particular region or not have it. So you can have 2 to the n choice. But then you are not interested in empty regions, so you subtract minus 1. So you have 2 to the n minus 1 dimensions. And for each one of these regions, you can compute entropy, entanglement entropy. So that means that entanglement entropy forms a 2 to the n minus 1 dimensional vector. And in fact, all possible entropy, all possible value of entropy realized holographically makes a cone, and that cone is convex. And the reason for that is the following. Suppose you have a gravitational solution, and suppose you assume the cosmological constant, you can adjust it. Say, for example, you can change n of the conformal field theory, etc., and to Hooft coupling of the conformal field theory, etc. So then you can actually scale, correspondingly, you can scale the entropy vector. Now, if you have two entropy vectors, one is realized by particular gravitational theory and another realized by particular gravitational theory, then you can consider, say for example, taking a direct product of the geometry, and that gives rise to linear combination of the entropy. So from that, we can see that entropy vector makes a convex cone. And inside of the cone can be populated by holographic construction. So basically, finding inequality is the same as finding the shape of cone, where the face of the cone corresponds to the entropy inequalities. So here is a way actually that we try to formulate computation of entanglement entropy inequality. So suppose you have this region A, B, C, etc. Then so we first compute all possible Ryu-Takayanagi surfaces by considering union of these regions, and that cuts the bulk geometry into pieces. And for each of these connected domain in the bulk, we put some vertex, and then connect them together like that. And then, so you have vertices, and you have links connecting them. And then I weight each of these links by the area of the corresponding segment of the surface. Okay? So you basically consider diagrams which are dual to Ryu-Takayanagi surfaces. Okay, and then here is actually a way you can compute Ryu-Takayanagi entropy. Namely, if you are interested in, for example, the Ryu-Takayanagi entropy for A and B, you consider all possible cut of these links. So for example, for this A and B, you can cut this link here, or you can cut this link here. And then you can just minimize it. And then there is a small lemma that you can prove that the total weight you compute in this way agrees with Ryu-Takayanagi formula. So this you can think of call that as discrete entropy. But this is nice because this reduces the program to finite program. Namely, for each given region, number of regions, you can actually prove that there is a universal graph model of 2 to the 2 to the n minus 1 vertices, which you can use to compute entanglement entropy for any combination of regions. This is very similar to the Mera type model, but it's sort of slightly different flavor. And because this is a finite program, you can and then basically different geometry just correspond to assigning different weight. So from that, it's obvious that the number of independent inequalities is finite, and holographic entropy cone is rational polyhedral. Thank you. So this way we can prove that the number of entropy inequalities is finite, and the question is then to enumerate all of them. Now, in practice, well, since this is a finite program, so in principle you can either ask your graduate student or computer to enumerate all of them. But in practice, if n goes to like 5, then it becomes not possible to do it. So what we did was actually to guess some inequality and actually certify that they are correct inequality and check whether they actually exhaust all the inequalities. So here is how we test it. So suppose you found a set of inequalities that we can verify that they are correct holographic inequality. How do we know that we have found all of them? Well, the idea is to construct extremal rays. So if you have rational convex cone, then there are particular entropy vector called extremal rays. Those are the rays that you cannot realize by sum of any two vectors inside of the cone. So if you identify extremal rays, then any other rays in the cones are positive linear combination of these things. So we identify these extremal rays, and then if so when you have entropy inequalities, you can find these extremal rays, and you can ask, can you find bulk geometry which realizes every one of these extremal rays? If you can do it, you are done, because then you can show that you can have entropy cone inside of which is totally populated, and so there are no more entanglement inequalities that you have to discover. So we have actually carried out this task for region 2, 3, 4, and found that actually in region up to 4, then all entropy inequalities come from non-Araki-Reeve or strong subadditivity inequality, and one new type of inequality called monogamy of mutual information, which was actually derived by Patrick Hayden and Alex Moroni and Matt Hedrick a few years ago. And then there is also a discussion of how to certify entropy inequality, but I don't have time to discuss. And using this way, we actually also found some new sets of inequality for 5 or more regions. So let me summarize. So we have found a complete set of holographic entanglement inequality for 2, 3, 4 regions. And this is interesting because this can be used to test when the conformal theory can have dual gravity descriptions. If you have conformal theory which violate these inequalities, then you know that these don't have smooth geometric realization, at least to the leading order in Einstein approximation. So that's actually all I wanted to tell you today. So there are some increasingly interesting sets of conditions that you can derive a set of constraints for low energy effective theories that give you that tells you whether such theory have consistent UV completion with gravity. And I think it'd be interesting to try to push this further and find more constraint. And in fact, finding constraint on the moduli space, and in particular putting constraint on even semi-stable vacua would be extremely interesting. So that's all I wanted to say. Thank you very much. Hi, Greg. Yes.
In your Venn diagram, if I look at the circle with the conformal field theories and then the subset with those that satisfy the gravity constraints, the ADS, the question is...
Yeah, so let me go over to the Venn diagram maybe. If I may.
Well, that'll do. Yeah, it's a simple question.
Yes.
What do you know about the relative volumes of those spaces?
Oh, okay. What do I know about the relative volume of, you mean comparing this and this, for example? Is that what do you mean by
I mean, comparing the volume of the CFT circle to the subspace of the CFT circle that intersects the ADS circle. So there's a volume, as you mentioned. There's a metric on the moduli space of CFTs. And you stated a conjecture about the finiteness of the volume. Actually, for my question, you don't need the finiteness, because I'm asking about the relative volume.
Okay, so let me try to understand. So the moduli space, geometry of the moduli space I talked about are already those which are low energy effective theory of consistent gravity theory. And those have finite volumes. I think that moduli space, all possible low energy effective action is infinite.
So you say my question doesn't make sense.
Well, in some sense, it's infinitesimal in that sense, because moduli space of infinite, all possible low energy effective theory is infinite, and then moduli space of consistent gravity theory is finite.
I'm trying to look at the volume of the moduli space of CFTs, and then there's a subspace of that moduli space of CFTs that satisfies these other
okay, so you're talking about this side, I guess that's. So you're asking how stringent this constraint is.
Yeah, I'm trying to ask
actually, I think it's pretty.
Volumes.
I think it's pretty stringent because, so for example, what we found is that the space. Well, I can only say about entropy inequality, but what we found is that for each number of regions, entropy inequality is finite, and the entropy cone is rational polyhedral. On the other hand, there are indications that for general quantum system, the entropy inequality is infinite. So that means that I think it's actually believed that entropy cone is smooth. So what this it seems to be numerical calculation seems to indicate that is that for regions 4 or more, the entropy, you have a smooth entropy cone, and in it you have a small rational polyhedral cone. And that corresponds to smooth geometry. Do I understand?
We'll talk about it later.
Okay.
So you talked about these entropy inequalities. Do you think that there is a local energy condition in the bulk that you could extract from?
No, yeah, so that would have been pretty interesting. But for example, here, so if you take second derivative, then you can actually have almost a local expression. And if you can invert this, then you can relate the energy density to the second derivative of relative entropy, right? So this. But I don't think it's true that relative entropy is convex in general. So it's actually the first derivative is non-negative, but I don't think there is a condition on the second derivative of relative entropy. So rather, for example, if you consider a class of gravitational theory where this energy density is positive, then the relative entropy probably would be required to be convex. So we actually discussed something to that effect in my earlier paper with Jennifer and the collaborators. But no, we try to see whether we can actually impose condition on local energy using this type of formula, but we didn't find. So all of the formula we have found for the integrated energy density, which might be actually what we should have expected, because we can actually give an invariant meaning to the notion of energy associated to domain. But the notion of energy associated to particular point is a more subtle concept. And but anyway, so we didn't find any condition like that.